Is the world as we see it the world as it really is? Today, we're going to dive into a really fascinating idea that the very tools we use to describe reality, our maps, our numbers, might be shaping our perception of it way more than we realize. So, I want to kick things off with this one question, because it's really at the heart of everything we're about to unpack. What if our rulers, our clocks, our coordinate systems, what if they aren't just these passive observers? What if they're actively creating the reality we think we're just measuring? To get by in the world, we have to create descriptions of it. It's best to think of these descriptions as maps. We use the map of physics, for example, not just to understand what's going on, but to predict what's going to happen next. And hey, because our predictions usually work out, planes fly, our phones can navigate, modern medicine works, we get really confident in our maps. We start to believe that the map is the territory, that our description is the absolute reality. But maybe that's a super dangerous assumption to make. Okay, let's zoom in on a core tool we use for all this, the coordinate system. It's basically just a grid that we lay over the world to describe where things are and how they're moving. But here's the crucial point. We choose the grid. Nature doesn't come with one pre-installed. So picture this. You're on a moving train and you drop a ball. From your point of view, it just falls straight down. Super simple. But to someone watching you from the ground, that very same ball travels in this big curved path, a parabola. So which description is the right one? Well, they both are. The actual event, the ball falling, is exactly the same. The reality didn't change one bit. All that changed was our description, and that was based on the coordinate system we picked for our own convenience. The world just does its thing, regardless of how we describe it. And this leads to a really, really important idea in science. See, if our descriptions can change that easily, we have to demand that some fundamental things don't change. They have to stay constant. Otherwise, all of our physics would just be, meaningless. There have to be things that are true no matter which map we're using. And that principle is called invariance. It's the golden rule, really. It just means that certain core properties of an object or an event have to stay the same, whether you're on the train, standing on the ground, or looking at it from Mars. This is how we keep our descriptions tethered to actual reality. So what kind of stuff are we talking about here? Well, for one, a vector, which is just something with a magnitude and a direction, like velocity, it has to keep its true length and its true direction. The core properties of an object can't just change because you decided to look at it differently. And of course, the underlying reality itself. That has to be invariant. Okay, so far so good. We have this rule, invariance, to keep our maps honest. But what if the very ink we use to draw the maps is flawed? What if the numbers themselves, the very building blocks of our coordinate systems, aren't as perfect as we think they are? This quote from our source material just illustrates the problem so brilliantly. I want you to think of numbers not as a smooth, continuous line, but as individual tiny grains of sand. And a whole coordinate system, well, that's like an entire beach made of that sand. Each number is its own discrete point. So if our numbers are like grains of sand, what about the space between the grains? Our entire numerical system, by its very nature, is discrete. It has gaps. And this means we might be completely missing everything that exists in those gaps. All right, now let's take this idea to its most profound and kind of mind-bending conclusion. If the numbers we use to measure everything have gaps in them, what on earth does that imply for our most fundamental measurement of all, time itself? We tend to think of time as a series of moments, right? One happening right after the other. A point in time. But what if that whole idea, the very concept of a moment, is just a side effect of our grainy numerical tools? Are we just seeing the individual grains of sand and calling them moments? Here's the radical thought. We normally assume that distinct moments in time are real, and we just use numbers to put a label on them. But what if it's the other way around? What if it's because we use these discrete numbers to describe the world that we get the impression of distinct moments? Our tool might be creating the very illusion we think we're measuring. And this all leads us to a final, really powerful idea. If our numbers are discrete, choppy, but reality isn't, then reality must be something else entirely. It has to be continuous, an unbroken flow. And when you think about it, this makes perfect logical sense. For anything to change, for an object to get from point A to point B, there has to be a continuous connection between A and B. If moments were truly separate, like little islands with nothing in between, how could anything ever happen? How could a cause ever lead to an effect? It couldn't. Which brings us to this beautiful, simple summary. Natura non facit saltus. Nature does not jump. It might sometimes look like it does, but that's only because of the grainy, gappy lens we're forced to use to view it. Reality itself is a smooth, unbroken process. And so we end right back at a question. We started by asking if our map is the territory. Now we've seen how our map-making tools, our numbers, might be creating features, like moments in time, that aren't actually in the territory at all. It just leaves you wondering, if we're wrong about something as basic as time, what else are we not seeing?